Hello everyone, I am Ankit Sharma, MSc Physics student at IIT Roorkee. Here I am presenting a video PPT on interaction of radiation with a matter. These are objectives. Firstly, I will introduce the topic, then I will discuss interaction of heavy charged particles, then fast electrons, gamma rays and neutrons. So what is radiation? Radiation is energy in form of waves and particles that comes from a source and travels through space or some medium. It generally four types on the basis of charge. It can be fast electrons, heavy charged particles, electromagnetic radiation, and neutrons. Also, radiation can be categorized into ionizing and non-ionizing radiation on the basis of energy. Ionizing radiation has enough energy to ionize atoms or molecules of a material that is harmful for the human body and environment. Now, the importance of the phenomena how radiation interacts with the matter are the basic and essential things to deal with the radiation, like to make radiation detectors and understand their mechanism, safety from radiation, to build shielding materials and various industrial uses. So interaction of heavy charged particles like alpha particles and protons. They have charge, so they interact with the matter primarily through Coulombic forces. Alpha particle interacts with the electrons, and two important phenomena, excitation and ionization, happens. Excitation, electron excite to higher energy state, and in ionization electrons leaves the atom and an electron at ion pair generated. When alpha particle gives a higher impulse to a material's electron, and emitted electron have sufficient kinetic energy, so that can create further ions. So these electrons are called delta rays. Now the rate of energy loss for heavy charged particle interactions is the differential energy as per penetration depth. It is also defined as linear stopping power. It is given by Bethe formula. It shows that energy loss is inversely proportional to particle's velocity. Means energy loss increases as the particle velocity decreases, or energy loss increases as the particle loses its energy. And also it shows that energy loss is proportional to charge of incident particle beam, charge of heavy particles. So the particles with the greatest charge will have a larger energy loss. Now, in comparing different materials as absorbers, energy loss depends primarily on electron density of the absorbers, and electron density increases with the high Z and high density material. Now it is the Bragg curve which represent energy loss with respect to distance of penetration, and it shows that for initial penetration, for initial path, it energy loses is proportional to 1 upon E, means inversely proportional to energy of heavy charged particle, and at the end of track it suddenly stops, means here alpha particle picks electrons and stops. So it deposits energy at a shorter distance and create secondary radiation. So we can use these properties to discriminate these heavy charged particles from other radiation. So also heavy charged particles have few picosecond in solids and few nanosecond stopping time in gases. And the range of heavy charged particles are very shorter. They can be stopped by a thin sheet of paper, or even they cannot penetrate a human skin. Now the interaction of fast electrons or beta rays. They loses their energy by collisional and radiative losses. In collisional losses, again ionization and excitation happens. Electron beam comes and collide with the electrons of absorbent materials. In this case, electron beam loses their energy at a lower rate than heavy charge particle and follow a more tortuous path and have a large deviation in electron path are now possible because the both masses are equal. The mass of incident electron beam and they collide with the electrons of absorber. So both have same masses. So here high scattering are possible. So in radiative losses, beam stealing effect happens when electrons comes under influence of a heavy nucleus electric field. Then it changes its path and radiate and emit energy and lose emit radiation and lose their energy. So the radiative losses are given by this formula. Here it shows that radiative losses are inversely proportional to particles mass, electrons mass. So uh, radiative losses are very less for particles, heavy charge particles, and radiative losses are proportional to energy and atomic number of absorbers. So uh, radiative losses has a small fraction of energy loss than collisional losses, and it is proportional. The energy loss of radiative losses are proportional to energy of the incident beam and atomic number of absorbing material. So the electrons beam of higher energy and absorbing material of a high Z value has a greater probability of radiative losses. Now the transmission curve shows that electron beam attenuates gradually as the increasing penetration depth, and the total path length is considerably greater than distance of penetration for electrons, and also it has higher penetration than alpha particles. Now one important phenomena, backscattering, also happens in the case of electrons, again because of electrons, both particles have same masses. The electron beam and the electrons of absorber materials have same masses though, so they have higher scattering. And in backscattering, when electron beam collides with the absorbing materials, it is the larger in electrons case, it has larger probability that some of electrons scattered back or reflects back. That we also should consider this effect in interaction of fast electron case. Now come to the interaction of gamma rays. So gamma rays are electromagnetic waves of energy in order around few hundreds of kilo electron volts. So gamma rays interact majorly via three phenomena: photoelectric, Compton, and pair production. In photoelectric absorption, a photon completely disappears and an energetic electron is ejected of this energy. It happens from one of its bound cells, mostly from K cells. And so, while photoelectric absorption, and there will be a vacancy in bound cell, and it is filled by a higher level electronic a higher electron. It is filled by an electron of high energy. Then there is a transition of high energy to low energy level that emits radiation, and that is called characteristic X-rays. Photoelectric absorption, the probability of photoelectric absorption is proportional to Z raised to power n. Z means the atomic number of absorber material. Z raised to power n around 4 to 5, so it is proportional to Z raised to power 4 and inversely proportional to energy of incident gamma ray. So the photoelectric absorption is predominant for gamma rays of relatively low energy and absorber materials of high atomic number. So we can use this property to deal with the gamma rays, like we we can use high Z constituents in the materials for make radiation detectors or to build a gamma ray shielding material. Now, Compton scattering, it is the most predominant interaction mechanism we are looking for. Like in the energy range, it is the most predominant interaction mechanism. Here, the photon collides with an electron or interacts with an electron and scatter out. Here, it transfer partial of its energy, and it is given by this relation. For small scattering angles, very little energy is transferred. The probability of Compton scattering per atom of absorber increases linearly with the Z. And previously we have seen that probability of interaction of photoelectric absorption is proportional to Z dash to power around 4. So for high Z values, means for high atomic number materials, the probability of photoelectric effect increases more than probability of Compton scattering. So we choose our materials accordingly for different purposes. There is a strong tendency of forward scattering at high values of gamma ray energies, means gamma rays of high energies scattered at lower angle and transferred less energy. And in Compton scattering, after one Compton scattering, the scattered photon will also undergo another Compton scatterings, because it transfers a partial of its energy. Now for pair production, it happens when the gamma ray energy exceeds twice of rest mass electron or 1.02 mega electron volt energy, but it predominates as the power increases into many mega electron volt range. In this interaction, the gamma ray photons disappears and replaced by an electron positron pair. Sometimes the reverse of this phenomena is also happens, means an electron comes and interact with a positron and annihilates. This is called annihilation, and this diagram represents the probability of these all three effects for gamma rays by comparing energy and atomic number of absorber material. Like the photoelectric effect dominates in the low energy gamma rays and high Z absorber materials. So there are also a scattering called coherent scattering or Rayleigh scattering. In this interaction, photon neither excites or nor ionize the atom, but it gets scattered. So there is no energy transform. The probability of this interaction is sufficient only for low photon energies and high Z absorbers. Since there is no energy transform, so and it is also less probable for high energy gamma rays, so we often do not talk about this interaction. Now the gamma ray attenuation. Gamma rays attenuates exponentially as increasing penetration, and they follow this relation. Here I note is the incident gamma ray intensity, and I is the intensity of gamma ray as the penetration depth T, and the coefficient mu is the linear attenuation coefficient that represents the probability per unit path length that the gamma ray photon is removed from the beam. We can also define like these quantities for gamma ray attenuation. The half value and tenth value layers. they represent a shielding property for gamma rays of some materials. 10th value layer means the required thickness of the material which attenuates 90% of incident gamma ray beam and only allows 10% to penetrate the material. Here the build-up factor is an important is very important. When in good geometry, the exponential relation follows by attenuating gamma rays, but when detector also detects the scattered gamma rays, then the proportionality of e raised to power minus mu t varies. So it is also important phenomena, and we also have to taken care about this while experimenting. Now the gamma rays have more penetration depth than alpha and beta particles. Now come to the interaction of neutrons. Neutrons are chargeless particles, so they can travel throughout many centimeters of matter without any type of interaction. We define a neutron cross section which represents the probability of neutrons with a for different mechanism like elastic scattering cross section, radiative capture cross section. It has units of area and measured in Born. This graph represents that cross section of neutrons for particular energies, and shows that neutrons for lower energy range has greater cross section, while then neutron of greater energy has lower cross section. We can also define a microscopic cross section that is similar for attenuation coefficient in gamma ray case. So we can divide neutrons in two categories: fast neutrons and slow neutrons. The borderline is 0.5 electron volt, which is the cutoff energy for neutron capture of cadmium. Now, how fast neutron interacts? The fast neutrons have very low reaction cross section. So mainly fast neutrons interact via elastic scattering, and we use this phenomena to moderate the fast neutrons. And to moderate the fast neutrons, we use the materials like HDPE, high density polyethylene, H2O, D2O, or wax, because they have low Z values. In the case of low Z values, neutrons transfer more its energy in elastic scattering. So here we can see that for some phenomena we are using low Z values, and for other radiation like for gamma rays we are preferring high Z values. Also fast neutron can do inelastic scattering, in which they excite the target nucleus and transfer more its energy. So we use elastic and inelastic scattering to moderate neutrons, and for moderate neutrons or slow down neutrons. And slow down neutron has a greater reaction cross section, and then we can the neutron reactions are possible. So neutron interact with the target nucleus and produce a recoil nucleus, means target nucleus will be in its excited states, and it can produce protons, alpha particles, or heavy fission fragments. These are some reaction of neutrons, like neutron interacts with boron and emits their emit alpha particle. These are the Q values of these reactions. Q values should be positive for these type of reactions. Neutron interact with the lithium and emits alpha particle. While interacting helium, it emits proton. So these are the elements which have higher neutron reaction cross section, and also gadolinium has largest thermal neutron capture cross section. So to deal with the neutrons, we have to put these elements in our material to make like neutron detectors or neutron shielding materials. So these are the interactions of various radiation with the matter, and we can take benefit of them according to our purpose. Like for gamma ray detection, we use high Z value materials. For to moderate neutrons, we have seen just we uses low Z materials, and these type of phenomena occurs. The source of this information is Knoll's book. Thank you.